You can find those slides on my webpage, robertabonacina.com, in the teaching section, and also in the colloquium webpage. This is the first part of, well, the course will be divided in 4 parts, even if will consist in 3 lectures. The first one will be an introduction, starting from the very beginning, so from the Lambda calculus, and introducing all the features of Martin-Löf type theory. Then in the second part, we will go into the details of our system of homotopy type theory, analyzing the main features, for example, the higher inductive types or the axiom of univalence. Then we will see how classical logic can be done in this system, which is by its very nature intuitionistic. And at the end, we will discuss the definition of equivalence, which is very important for introducing univalence, but is also quite tricky, as we will see. So now a bit of literature. We will, the main part, the majority of those lectures will be based on the book Homotopy type theory, which can be downloaded on its website freely. But the first part, so the history of Lambda calculus, is based on a paper by Cardone and Hindley, which is so the history of Lambda calculus and combinatorial logic. So today's lecture, which is the introduction, will begin, as I said, with the history of the Lambda calculus. Then we will introduce in details the simple theory of types and stress the propositions as types interpretation, which is the reason why we say that the system is intuitionistic. Then we will introduce the dependent types and so see what Martin-Löf type theory is. And at the end, we will study propositional equality, which is a very important feature of homotopy type theory, already present in Martin-Löf type theory. So starting from the history, in 1928, Church defined the Lambda calculus, which is a formal system whose purpose was to provide a foundation for logic. But a few years later, 2 of the students, Kleiner and Rosser, found a paradox, and they proved that when the Lambda calculus, which is a system per se, is seen as a system of logic, then it is inconsistent. So Church in 1940 reformulated his theory and introduced the simple theory of types, which is based on Lambda calculus again, but introduces the feature of types, which allows to avoid this paradox. Then in 1958, the propositions as types isomorphism was introduced by Carré and Fegé. And this isomorphism, as we will see, proves that the simple theory of types works very well as a logic. And then this isomorphism was extended by Howard to proofs and terms. So all of this is based on the simple theory of types, which was extended by Martin-Löf to Martin-Löf type theory, which is a constructive type theory with dependent types. And then Weizsäcker and a lot of other mathematicians extended Martin-Löf type theory to homotopy type theory, which is the main system we are interested in. So let's start with the simple theory of types. The main types of this theory are 1, 0, the product type, the sum type, and the arrow type. So the type 1 is the type with only one term, which can be seen as the set with only one element. 0 is the empty type. Then we have the product type, whose terms are the couples, the pairs, and are introduced, are the pairs, for example, the terms of the product type A times B are the pairs of terms of type A and the terms of type B, which then we have the sum type, which can be seen as disjoint union, and so the canonical terms are the inclusions of the terms of type A and type B. And then we have the arrow type, which is the type of functions from type A to a type B. So if we have a term small b of capital B and a variable x, we can obtain the lambda terms, lambda x of type A dot B, of type A to B, which is also the construction which gives the name to the lambda calculus. We introduce now also the two projections from the product type. So we have that the first projection maps terms of the product type into terms of the first type of the product, and the second projection maps into the second. So we have that, and in particular, we have that the projection of a couple AB, the first projection maps is the term A, and the second projection is the term B. Those types originate the propositions as types correspondence, as I said. And we have that the type 1 is mapped to the truth. The type 0 is the falsity. The product type is conjunction. The sum type is disjunction, and the arrow type is implication. This extension, as I said, extends to a correspondence between the constructor for the terms of the types and the inference rules of logic. And so it becomes a correspondence between the terms of the type and the proofs of the corresponding proposition. We will see this in details for the introduction rules. So, for example, for the product type, let's see the introduction rules for the product type and the logical conjunction. We see that they have the same structure. So, to introduce a pair of a product type, we need to have a term A of the first type and another term of the second type, which is what happens with logical conjunction. So to obtain A and B, we need to have a proof small a of the type A and the proof small b of the type B. So what we have is that a type is inhibited, so it has a term when the corresponding proposition is provable. And it holds that every distinct term of a type corresponds to a different proof of the proposition. So the interesting thing is not only that the proposition is provable, but also we are interested in knowing which is the proof. Something similar holds for implication and the arrow type. So to construct a lambda term, we need to have a variable x and a term small b of type capital B. And analogously, to obtain an implication, we need to have a proof mapping the proposition A to the proposition B. And here, in a sense, we have that the label star in A stands for x, which is our variable. Here we have an assumption as we have a variable here. Finally, for coproduct and logical disjunction, well, we have two rules, two introduction rules. Let's just analyze the first one. if we have a term small a of type A, we can construct this inclusion, which we call the I1b of A, which is of type A plus B. And this corresponds to saying that to obtain a logical disjunction A or B, we need a proof small a of the proposition A. Here we have to notice that this introduction has those labels which indicate to which type belongs the term A, from which it is introduced, from which it is constructed, and we also indicate which is the other type. This is important because our theory is constructive. So we have that each term is not only a statement which says that the type is inhabited, and so that the proposition is provable, but it's also a witness which show how to construct this inhabitant. So if we have a canonical term of this coproduct type, we also know how to construct it and from which term from which type it has been constructed. So it holds that if we choose the right logic, this correspondence allows to identify the logic with a calculus system. And what happens is that the right logic in this system is intuitionistic logic. This logic has the same rules of classical logic, but it doesn't have the law of excluded middle. So we don't have that A or not A is always derivable. And so we also have that not A implies A is not provable. And so we cannot use the reduction ad absurdum. So as happens with types, we have that a proof of a proposition in intuitionistic logic says not only that the proposition is true, but also contains an algorithm to obtain the context of the proposition. So, for example, if we prove in intuitionistic logic that a certain equation has a solution, we don't know only that this solution exists, but in a sense, following the proof, we are also able to construct this solution. Sorry. Now we have seen this isomorphism between the simple theory of types and propositional intuitionistic logic, and we may be interested in extending this isomorphism to first order intuitionistic logic. And to do this, we have to introduce the notion of dependent types. So what we have is that the concept of function from A to B can be extended to a more general case, which is the case in which, well, the domain of the function is A, but the codomain has a dependent structure. So we need to have that capital B is a function with domain A. And so a function f from A to B can be defined such that the codomain of f, so f of A is in a different type. They have evaluated in a, so the type in which f of A lives depends on the choice of small a of the term. And the same construction can be done for pairs. So this allows to introduce two other types, which are the pi and the sigma types. The pi types, pi x of type A, b of x, is the type of dependent functions, and the sigma type is the type of dependent pairs. So they are generalization of the two types we have already seen of arrows and product, and they reduce to those types when the type B does not depend on the variable x in A. Here we have that the canonical terms are defined in similar ways from arrows and product. So a canonical term of a pi type is constructed again from a term small b of type B, which depends on a variable x of type A, and we have again a lambda term, while a pair term of a sigma type is constructed starting from a term small a of the type A and another term small b, which this time is a term of the type B of A. So let's see a couple of examples. We have that this is a dependent pair which contains all the n tuples of naturals for each small n for each natural number small n. And as an example of a term of dependent product, we have this zeros term, which is such that zeros evaluated to which is applied a natural number n is the vector of zeros of length n. So those are two examples of the types. And those types allow to extend the correspondence. We have already seen the first 5 correspondence, and now we have that the pi type can be associated to the for all, and the sigma type is isomorphic to the existential operator. Again, the introduction rules behave accordingly to this isomorphism. So, for example, we have seen that to introduce a pair in a sigma type, we need to have small a of type A and small b of type B of A. Well, to introduce the existential quantifier, we need to have a proof small a of the type A and another proof small b of the proposition B in the case small a. Again, as for the sum type, we have to notice that a term of a sigma type carries a lot of information. So it doesn't only say that a certain B of x is inhabited, but it also allows to construct which is the term A such that B of A is inhabited. And this is a consequence of the constructive nature of the theory.
So informally, one could say that we have a witness of type A and we have a proof that that witness has the property B, essentially, right? There exists an A such that
there is an A such that the proposition B of A holds, because the property B depends on.
Yeah, so we have a witness and we have a proof that that witness actually is a witness.
Yes.
Thanks.
Welcome. So this was the idea for dependent types, and now we can arrive to Martin-Löf type theory. This type theory consists in the simple theory of types extended with pi, sigma, natural numbers, and an equality type, plus an infinite hierarchy of universes. So natural numbers are defined inductively, as one could expect. We say that n is a type, that 0 is a term of type n, and that if n is the term of type n, then also its successors. Then we have this infinite hierarchy of universes. They are Russell-style universes. So we have that the first universe, U0, is a term of type U1, which is a term of type U2, and so on. And this hierarchy is cumulative. So we have that if A is a term of type Ui, it also is a term of type Ui plus 1. Actually, this construction formalizes the notion of type. And we say that a term is a type if it is a term of a certain universe. Now, universes are indexed, but we will not always write the index only when it is relevant. Now, let's introduce the last important type of Martin-Löf type theory, which is propositional equality. We have that given a type A and two terms of this type, A and B, we introduce the propositional equality type A equal B in A. And we have only one canonical term. Well, not all the equality types have a canonical term, only the one with the same endpoints. And this canonical term is the reflexivity, ref A, which says again that equality is reflexive. The idea behind this type is that if there is a term of a type A equal B, then the two terms are equal. We have that, well, if A and B are closed terms, in general, their equality type is empty when the two terms are syntactically different up to conversions. But it is always possible that an equality type contains other terms other than ref. And we will see with the higher inductive types how this is done. So we have seen the structure of the other canonical types, which was quite straightforward to analyze. This is not the same for equality. So they wondered how equal A behaves as a set, but the solution in this case was to focus not on sets but on other mathematical theories. So Stryker considered from this interpretation category theory, and he interpreted equality types and as infinity groupoids. So he said that a term P of type A equal B is a morphism from A to B, which are interpreted as objects, and a term X of type P equal Q, where P and Q are terms of type A equal B, is another morphism from P to Q. This construction, of course, can be iterated as much as you want. Voivodovsky did the same, but using homotopy theory, and so seeing P as a path from A to B again. The construction is the same. The two constructions just live in different words. say. Another feature of Martin-Löf type theory is the notion of induction. Well, in that we have already seen induction for natural numbers. In naturals, it tells that to prove a statement on all naturals, it is enough to prove it for 0 and for the successor of n, knowing that it holds for n. And they generalized this idea, saying that to prove a statement about all the terms of a certain type, what we can do is to prove it only for the canonical terms. So, for example, for the sum type is easy, and so to prove that A type C, which depends on A plus B, is inhabited, we just can show that a term of C can be constructed from the two inclusions. So actually from a term small a of type A, which is easily included in A plus B, and another type term of type B, which again can be easily included. If we can prove this proposition from just those two cases, we can deduce that it holds for all the terms of type C. This is indeed a very useful property, which we can see as how it's used for equality, for propositional equality. So let's prove, for example, that propositional equality is symmetric. So we want to prove that for every type A and A and B of type A, there is a function from the equality type A equal B to the equality type B equal A, which maps a type P of term A equal B to its inverse P to the minus 1, and such that the inverse of reflexivity is again reflexivity. We can do this using induction. So we have A and B of A, B, and P, and we want to construct P to the minus 1. But by induction, we can just do this in the trivial case. The trivial case is the one in which B is just A, and so P is simply reflexivity. So it is, we have that the inverse of P has to be of type A equal A, and so it is easy to take the inverse of refl, since P again is refl, as again refl, which satisfies our requirement and allows to obtain the general case by induction. So in a similar way, it can be proved also that propositional equality is transitive, so that given A, B, and C of type A, there is a function which maps a term P of type A equal B and a term Q of type B equals C to their composition P dot Q of type A equals C, and such that the composition of the reflexivities is again reflexivity. And we also can prove that those operations, so composition and inversion, are well behaved. So if we have A, B, C, and D of type A, and we have the path B from P, sorry, from A to B, Q from B to C, and R from C to D, then we have that reflexivity. The ref on B and A are respectively the we have that P is equal to P composed to roughly B, and that P is equal to roughly A composed to P. Then we have that pi to the minus 1 composed to pi to P is equal to roughly B, and P composed to P to the minus 1 is reflexivity on A. Then we have that the inverse of an inverse is the identity, and we have that composition is associative. We're not going to prove those results, but they can be proved by induction, similarly to what we have seen for the previous results. We also have that functions f from A to B behave functorially on path. So we have that they respect equality. Or from a topological point of view, we may say that those functions are continuous. Indeed, we have that if f is a function from A to B, and x and y are terms of type A, then there is this operation AP of f, which maps the terms of type x equal y to the equality terms of f of x equal f of y. So in a sense, we can lift the path from the equality in A to the equality in B through this function. And we have what we would expect, so that for each term x of type A, the application of f to ref in A is reflexivity of f of x. We will sometimes abuse notation and write f of p instead of AP f of p. And again, the proof is easy by induction, because it is enough to prove it in the very trivial case in which P is the reflexivity on X. And so in this case, of course, it is enough to define APF of P as the reflexivity on f of X, which is of the right type f of X equal f of X. And the general case follows by induction. Now, this result can be generalized to dependent functions, but is not straightforward. Indeed, we would like to prove a dependent version of the previous lemma, but we have that if given a certain path P from X to Y, it holds that f of X and f of Y may be terms of two different types, B of X and B of Y. And so we cannot construct the equality type as we have done before. So here, what we do is to use the path again as a way to relate B of X and B of Y. And indeed, we have that given a family of types, B from A to the universe, so which simply is a dependent type, and given a path P from X to Y, then can be obtained a function P star from B of X to B of Y. Again, by induction, we assume that P is a reflexivity, and so it is enough to take P star as the reflexivity, sorry, the star of reflexivity as the identity function. So in this way, we obtain this function P star, which is called the transport function. and which is very useful to generalize lemma 7. Indeed, obtaining from the transport function, we can obtain this dependent version of AP. And so we have that if f is a dependent function of a pi type, we have that there is a map APDF, which maps each term P of type A equal X into this other, a term of this type, which is P star of f of X equal f of Y. Oh, sorry. And this can be done by induction, again, assuming that P is reflex. And in this case, the equation holds judgmentally, so it's the reflex star of f of X is trivially equal to f of X.